The first thing I want to talk about is this idea of moving from 2 dimensions to 3 dimensions, and it's surprising how similar our formulas and that become. So at the moment we're used to working with a 2-dimensional Cartesian plane, and it looks something like that, and we know it's got 2 axes which we call x and y usually, 1 coordinate plane, and it's divided into our 4 quadrants, starting where they're both positive and going around anti-clockwise. And then any point, of course, we can define by its coordinates, an ordered pair we sometimes call them. Now for 3 dimensions we move to a Cartesian space. Now I've drawn it up this way, and this is probably one of the more common ways of doing it, where you'll see that our Cartesian plane is lying flat, and then the z-axis is coming through it. We tend to make the octant, now because there's 8 of them, the positive one, the one that's sort of facing us. So that's why the x looks like it's going down if you think about it, but it's actually, we're saying the positives are going that way. So we now have 3 axes, x, y and z. But we have 3 coordinate planes. There's the one we're used to seeing, the xy, but now there's an xz plane and a yz plane as well. And it's broken up into 8 octants. The first octant being the one where they're all positive. And again, we go around anti-clockwise, but then we drop down to the negatives and go around anti-clockwise again. But our point now is defined by an ordered triple, and we do it in the logical order, x, y, z. Problem is, we're used to working on a piece of paper which is a flat surface which is 2-dimensional. It's very hard to draw a 3-dimensional thing. I plot P there, and it really is hard to imagine where it is. So sometimes we'll just draw a rectangular prism in. We can feel where it is. And so OP would be the diagonal of that rectangular prism. And by putting that in, you can sort of now feel where the point is sitting on the Cartesian space. We know in 2 dimensions, lines parallel to the coordinate axes. Well, if it's parallel to the x-axis, we'd get y equals, for this one, 3. And if it's parallel to the y-axis, for this one, we'd get x equals 2. Well, now we have planes parallel to the coordinate planes. And so here's my point, 2, 3, 1. If it was parallel to the xy plane, there we go, then it would be z equals, and in this case 1. Because every point on that plane would have the same z value. It would be 1. If I was to draw in the one parallel to the xz plane, then every y value on that plane would be the same. So y equals, in this case, 3. And then we have a third one, a plane that's parallel to the yz plane, put that one in, and that would be x equals 2. So it's the same idea, but we're pushing the idea through to another dimension. So the line now becomes a plane. 2 very familiar formulas that we work with in 2 dimensions. The distance formula. So in 2 dimensions, we're used to seeing it. There it is. Square root of x2 minus x1 squared and so on. In 3 dimensions, if I want to find the distance between these 2 points, how would I do it? Again, I'll draw in a rectangular prism, so I've got a feel for everything there. Well, I can still create a right-angled triangle, because you'll remember that's how we did it in 2 dimensions. We created a right-angled triangle, used Pythagoras. I can still do that. And this side, I know, would now be the difference in the z values. The third side here, lying on the bottom of the prism though, what would that be? Well, if I was just to project it down so it's sitting on the xy plane, it then would be our traditional distance formula. That length. Those 2 would be the difference between the x values and the y values, meaning the hypotenuse would be our formula, the square root of x2 minus x1 squared and so on. But that would be the length of the base of this triangle, which means the distance then becomes the square root, that side squared, plus the one we called z2 minus z1, and something very nice happens. And you can see the similarity between the 2. Essentially, it's still the same formula, but we've now added in the 3rd dimension. We've got the difference in the z values as well. Well, midpoint formula, which in 2 dimensions we know is this. Well, what was it? We said it was the average of the points. So the average of the x values, the average of the y values, push it through to 3 dimensions. We now get this 3rd coordinate, which is the average of the z values. So that starts us with that idea of pushing through to 3 dimensions.